Welcome back to the isaaclab tutorial series. In part 3, we are going to continue building our simulation setup and more specifically launching our Jetbot to the track with data collection capabilities. Inside the repository, open up your code editor of choice and create the following Python files in the RC track folder we created earlier. RC track params, jetbot config, create RC track, and run FPV. Go ahead and paste in the codes provided in the GitHub repository called tutorials, also linked down in the description below. Just make sure to replace the paths in the file jetbot config and run FPV. Once you have pasted all the code, make sure to hit save. Alright, let's start by looking at the script that contains all the tunable parameters for the track. First of all, everything is in meters. We define the outer length, width, and corner radius of the track's rounded rectangle, as well as the visual properties of the dashed center line, the dash length, the gap between dashes, the line width, and even the physical line thickness. In jetbot config, we define the configuration for loading the jetbot robot as an asset into the scene. Jetbot USD path points to wherever we saved the jetbot earlier. Then jetbot config wraps that into a USD file config object from isaaclab, telling the simulator how to load it. These two files make it convenient to make tiny changes to the environment later on. Moving on, create rctrack.py builds our entire rctrack world inside isaacsim. This file is responsible for launching the simulator, generating the ground plane, drawing the line, and finally placing the jetbot at its starting position. At the top, the script defines the argument parser so we can optionally save the generated world to a USD file. Then we launch isaacsim using isaaclab's app launcher. Next, we pull in two configuration objects, track config and jetbot config. Then we get to the helper functions. Create ground just spawns a simple black plane. The function create track calls the functions build centerline points and spawn dash that give us track points and cuboids respectively. Finally, a clean dashed line track is rendered. The function spawn jetbot drops the jetbot model onto the track aligned with the top straight. We also apply suitable lighting, hide the default environment geometry, and finally export the entire world to USD. I personally find the last script, runfpv.py, the most interesting one as it makes the jetbot generate data for us. It loads the world we generated, starts isaacsim in real-time mode, and connects to the FPV camera we previously created. This camera provides a live 1280 by 720 FPV feed at 60 Hz. To control the robot's wheels, the script uses the simple jetbot driver class. It directly accesses the left and right wheel joints through isaacsim's dynamic control interface, and it also lets us read the jetbot's current XY position in the world. Next comes the vision component, handled by the compute line offset function. It processes the entire RGB image, converts it to grayscale, thresholds the bright pixels, and finally computes the mean horizontal position of the detected line. That value is normalized between -1 and +1. If no bright pixels are found, the function returns none, which means that the line is lost. The main control logic lives inside the line follower class. It implements three behaviors. First, normal line following. When the line is visible, steering is simply proportional to the offset. Second, line search mode. If the line is lost, the robot spins in place to try to find it. Third, random perturbations. Whenever the jetbot enters the top straight section of the track, based on its current XY position, the controller starts a short perturbation interval. During this time, it applies a fixed, randomly chosen steering value. This is a simple but effective way to give us representative training data of the track. We don't want every training frame to look exactly the same. The perturbation system includes two failsafes. If the line disappears during perturbation, or if the offset becomes too large, meaning the robot is drifting too far off the track, the perturbation ends immediately. The main simulation loop runs while isaacsim is open. For each frame, the script advances the physics several steps to speed up the simulation, then renders once. It reads the latest FPV image, passes it to the controller, updates the wheel velocities, and optionally shows a debug overlay. It can also save FPV frames at a user-defined interval. These are all arguments that the user can tweak, and we will soon see that in action. Let's start the deployment by generating ourselves a track. Run the following command. This will open isaacsim and show the track along with our custom Jetbot. The track is saved automatically to the directory called worlds, so no need for further manual saving. And if we open the worlds directory, we can see that the track is successfully saved. Let's continue by closing isaacsim using Ctrl+C on Powershell. Before running the simulation, install opencv using the following command. Note that the required version of opencv might change in the future, but if this is the case, you will see a warning on your screen. Let's run the simulation by using the perturbation length of 0.75 seconds. Save every 30th frame and with double the normal speed. The debug whiz argument allows us to see an FPV preview of the saved frames. We should now see the Jetbot driving around our track together with an opencv preview window. Let's remind ourselves that the offset measures how far off the line segments are from the image center. The steer value is derived from the offset value, and the mode remains auto unless the Jetbot is located at the bottom right part of the track from our current perspective. If we navigate to the FPV directory inside Outputs, we can see the saved frames. These can then be used for training machine learning models. That's all for this video. Thank you so much for watching, and I will see you guys in the next one. Peace!